Welcome back to Notes of Curiosity, exploring ideas that matter. We're picking up where we left off in our deep dive into mass by Jim Baggott.
It's fascinating how he takes us through centuries of thought on this idea of mass, It really shows how much our understanding has changed.
Yeah, definitely. And in the second half of the book, chapters 9 through 16, things get, well, pretty mind-bending. We're going into relativity, quantum mechanics, even the mysteries of the dark universe.
Baggett has a real talent for making those complex ideas understandable. He doesn't skip the details, but keeps the bigger picture in focus, helping us see how everything connects.
Absolutely.
Yeah.
Last time we talked about how Newton's laws changed how we think about objects moving. But even Newton couldn't quite answer the question, what is mass, really?
Right, and that's where Einstein comes in. In Chapter 9, Baggett introduces us to Einstein's theories of relativity. They completely changed how we understand not just mass, but energy, gravity, even space and time itself.
And one of the most famous equations ever comes from Einstein's special relativity, EMMCRR. It's so simple, yet it has such huge implications.
It tells us that mass and energy are basically the same thing, two sides of the same coin. And that idea was key to understanding nuclear energy, how stars work, even the Big Bang itself.
Mind-blowing, right? That a tiny bit of mass can become so much energy.
And then there's general relativity, which changed how we think about gravity. Baggett explains how Einstein showed that gravity isn't really a force, but a warping of space-time caused by mass and energy.
It's like imagine a bowling ball on a trampoline. It makes the fabric sag, right? That's how we can picture mass warping space-time.
Exactly. And other objects, like planets, are then drawn along that curvature created by the massive object. It's a completely different way of looking at gravity. And what's amazing is we've actually proven this warping of space-time through experiments.
It's like how GPS satellites have to take both special and general relativity into account to give us accurate locations. Proof that these theories aren't just abstract ideas, they really affect our world.
Absolutely. But even with these revolutionary theories, there were still some puzzles to solve. As Baggett points out, neither Newton nor Einstein could explain inertia. Why objects resist changes in motion.
It's like they have this built-in stubbornness. You try to move them, and they push back. Such a basic concept, and it still has physicists stumped.
It does. And that takes us to the quantum world, which Baggett gets into in chapters 10 through 13. This is where the normal laws of physics start to break down, and a whole new set of rules governs how matter behaves at the atomic and subatomic level.
It's like going through a looking glass into a world where things aren't quite what they seem. Particles act like waves, energy comes in little packets, and everything is governed by probability.
One of the big ideas Baggett explores is wave-particle duality. He writes, "It's not that a particle sometimes acts like a wave and sometimes acts like a particle. It's that it's both, all the time." And this isn't just some theoretical quirk. It has huge implications for understanding the nature of reality.
It's like the universe is playing hide and seek with us. We try to pin down a particle, and it's like, nope, now I'm a wave. It's enough to make your head spin.
And just when you think you're getting a handle on wave-particle duality, Baggett throws another curveball at you. Heisenberg's uncertainty principle.
Right, the more we try to measure one thing about a particle, like its position, the less we can know about something else, like its momentum. It's like there's a limit to how much we can know about the quantum world.
It's not that our instruments are bad, it's a fundamental principle, about reality at the quantum level. As Baggett puts it, the uncertainty principle isn't about our limitations as observers. It's about a fundamental fuzziness built into the fabric of reality at that level.
So we have energy coming in bundles, particles behaving like waves, and this inherent fuzziness in reality itself. Is there anything else that can surprise us in this strange quantum world?
Oh, plenty more. Baggett then takes us into the even weirder realm of quantum entanglement.
Ah, yes, this is where it gets spooky. Two particles can be linked, even if they're super far apart, so that their properties are correlated. It's like they're communicating instantly across space.
Einstein called it spooky action at a distance, because it seemed to break the idea of locality, that an object can only be influenced by what's right next to it.
But experiments have shown that quantum entanglement is real. So what's going on? Does information really travel faster than light?
That question has been bugging physicists for a long time. The usual interpretation of quantum mechanics says it's not about information traveling faster than light. It's that these entangled particles share a single wave function that isn't limited to one place.
So they're not sending signals to each other. They're connected in a way that goes beyond our normal ideas of space and time. Like they're two parts of one thing, no matter how far apart they are.
Exactly. And this non-locality is one of the most profound implications of quantum mechanics. It suggests that the universe is interconnected in a way we're only beginning to understand.
So now we have these two revolutionary theories: relativity, describing the universe on the grand scale, and quantum mechanics governing the subatomic world. But can we put them together?
Oh.
Are they compatible?
That's the big challenge in physics. Finding a unified theory that combines relativity and quantum mechanics. And that's what Baggott explores next in the book.
He goes into the search to unify the four fundamental forces of nature: gravity, electromagnetism, the weak force, and the strong force.
Yeah.
It's like trying to put together a giant cosmic jigsaw puzzle.
And he introduces us to the standard model of particle physics, which has been incredibly successful in describing three of those forces.
The standard model is like the periodic table of particle physics, isn't it? It lists all the fundamental particles and how they interact.
It's a huge achievement. But here's the thing. The standard model doesn't include gravity. We haven't figured out how to fit gravity into a quantum framework yet.
So the standard model is like this beautiful puzzle, but there's a missing piece: gravity. It's like having a delicious cake, but without the frosting.
That's a good way to put it. And there's another missing piece that Baggott explores. Where does mass actually come from? If Imam tells us mass and energy are interchangeable, what gives particles their mass in the first place?
It's the question we keep coming back to: the origin of mass. It's this fundamental property that we can measure, but we're still trying to understand its true nature.
And the answer, according to the standard model, lies in something called the Higgs mechanism. Imagine a field that permeates all of space, the Higgs field. Particles interact with this field, and it's these interactions that give them mass.
So it's not like particles are born with mass. It comes from their interaction with this Higgs field.
Exactly. And the Higgs boson, discovered at CERN in 2012, is the particle associated with this Higgs field.
So the Higgs boson confirms that the Higgs field exists, and the Higgs field is what gives particles mass. It's like a cosmic dance, where the interaction between particles and this invisible field creates the property we know as mass.
That's a great way to picture it. But hold on, the story doesn't end there. Baggott throws us another curveball in chapter 16, dark matter and dark energy.
Right. This is where we really bump up against the limits of what we know. We've discovered that all the matter we can see, stars, planets, galaxies, even black holes, makes up just a tiny part of the universe's total mass and energy.
It's like realizing that the world we experience with our senses is just the tip of the iceberg. There's this whole hidden universe out there made of stuff we can't see or directly interact with.
It's a humbling thought.
Mm.
We've come so far in understanding the universe, but we're still faced with these enormous mysteries.
And that's what makes science so exciting. There's always more to explore, more to discover. We'll dive into these mysteries of dark matter and dark energy in the next part of our deep dive.
Welcome back to Notes of Curiosity. We're continuing to explore those mind-bending ideas in Mass by Jim Baggott, especially those mysteries, dark matter and dark energy. It's wild to think that all the stuff we can see, stars, planets, galaxies, it's just a tiny sliver of the universe's total mass and energy.
It really does make you rethink what's real, doesn't it? It's like we've been living in this tiny, well-lit room, and suddenly someone opens the door to this huge, dark landscape we never knew was there.
Yeah, exactly. And in chapter 16, Baggott takes us into that unknown territory. He starts with dark matter. We can't see it directly, but we know it exists because of its gravity.
Right. Astronomers first started getting hints of dark matter way back in the 1930s. They were looking at galaxies in clusters, and these galaxies were moving way faster than they should have been if you only considered the visible matter.
So like there's some kind of invisible force holding those galaxies together, keeping them from flying apart.
Precisely. It's as if there's this scaffolding we can't see surrounding those galaxies and clusters, providing the extra gravity they need to stay together.
And we see the same thing happening inside individual galaxies too, right? Like the stars in the outer parts of spiral galaxies, they're orbiting faster than they should if the only matter was what we can see.
That's right. When you look at the rotation curves of galaxies, the graphs that show how fast stars are orbiting at different distances from the center, they don't match up with the visible matter. It's like each galaxy is wrapped in this halo of invisible matter.
Okay, so we have all this evidence for dark matter, but the big question is, what is it made of?
Now that's the question that's been puzzling physicists for ages. There are lots of possibilities being thrown around. WIMPs, axions, sterile neutrinos. Each of those hypothetical particles has its own weird properties and ways of interacting, or not interacting, I should say, with ordinary matter.
It's like a giant cosmic treasure hunt, with scientists all over the world searching for clues about dark matter.
And it's not just about finding these particles, it's about understanding how they behave, how they clump together, how they've influenced the structure of the entire universe over time.
Because even though we can't see it, we know dark matter has played a huge role in shaping the cosmos, right?
Oh, absolutely. It's like an invisible hand sculpting the universe, guiding how galaxies and clusters formed.
So we had this mysterious dark matter making up a big chunk of the universe. And then Baggett introduces yet another mystery, dark energy.
Ah, yes, dark energy. If dark matter is like the invisible scaffolding of the universe, dark energy is this weird force that's actually stretching the fabric of space-time itself, making the universe expand faster and faster.
It's crazy to think that just 100 years ago, astronomers thought the universe was static. Then Hubble came along and showed that galaxies are moving away from us, and the farther they are, the faster they're going.
Hubble's discovery was huge. But then, in the late 1990s, two teams of astronomers made an even bigger discovery. This expansion isn't just happening, it's accelerating.
It's like we're on this cosmic roller coaster that keeps getting faster.
A great analogy. And the force behind that acceleration is what we call dark energy.
But what is dark energy? Some kind of anti-gravity? Or something even weirder?
Well, that's the million-dollar question, isn't it? One idea is that it's this thing called a cosmological constant, a kind of energy built into space-time itself. This constant would create a kind of repulsive force, pushing against gravity.
So you're saying empty space itself has energy, and that energy is pushing the universe apart?
That's one way to think about it. Another possibility is that dark energy is a dynamic field, something that changes over time.
Meaning dark energy could be getting stronger or evolving in ways we don't understand yet.
Exactly. And figuring out what dark energy really is, that's one of the biggest challenges in cosmology today.
It's pretty amazing we've come so far in understanding the universe. But these basic mysteries, dark matter, dark energy, are still right there in front of us.
And it's these mysteries that keep pushing science forward, making us develop new theories and build better tools to explore the cosmos.
Jim Baggott really captures these mysteries en masse. He leaves you feeling this sense of wonder and wanting to learn more.
He does, doesn't he? It's a good reminder that science is a journey, not a destination. There's always more to learn, more to explore, and more to discover about the universe we live in.
Well, we've covered a lot in this deep dive into the hidden universe of dark matter and dark energy, but there's still more to think about. In the final part of our deep dive, we're going to zoom out a bit and consider what all of this means for how we understand the universe and our place in it. Welcome back to Notes of Curiosity. It's amazing, isn't it, how diving into Jim Baggott's mass has given us not just the science, but a whole new way of thinking about, like, our place in the universe.
What really struck me is how Baggott connects these big ideas like mass, dark matter, dark energy to the whole story of how the universe evolved. It's pretty masterful.
Yeah, for sure. So in this final part, let's take a step back and look at what we've learned. We started with mass, something we thought was simple, just a measure of how much stuff there is, but it's turned out to be way more complicated than that. It's tied up with energy, space-time, and those mysteries we talked about, dark matter and dark energy.
It really shows the power of science, right? Always pushing at the edges of what we know. Every time we think we've got a handle on things, the universe throws us a curveball.
Exactly. And one of the biggest curveballs is realizing that all the stuff we see and touch every day, it's just this tiny fraction of what's really out there.
Baggott puts it perfectly in chapter 16. He says, the universe is not as we perceive it. Basically, we're blind to most of what the universe is made of, dark matter and dark energy.
It's like finding out that the world we know is just a thin sheet laid over this much deeper, more complex reality.
And that deeper reality is actually shaping the fate of the universe. Dark matter, with its gravity, is like a sculptor, guiding how galaxies and clusters form.
And then there's dark energy, this strange force that seems to be pushing everything farther and farther apart, accelerating the expansion of the universe.
Like a cosmic tug of war, with these unseen forces battling it out.
So after centuries of trying to figure it out, have we finally understood mass?
Well, Baggott doesn't give us easy answers in mass. What he does is leave you with this sense of awe and the realization of how much we still don't know.
He writes, and this is such a great line, "The quest to understand mass is a journey without a final destination." It perfectly captures how science is always ongoing, always searching.
And what drives that search is curiosity, that need to unravel the mysteries of the universe.
Exactly. And mass is like an invitation to join that search, to think about how those tiny particles are connected to the biggest structures in the cosmos.
It reminds us that even something that seems ordinary, like the idea of mass, can make us question the very nature of reality itself. Where do we fit into all of this?
So if you're the kind of person who likes those big questions, who wants to explore the frontiers of physics and cosmology, I can't recommend Jim Baggott's math enough.
It's definitely challenging, but it's so worth it. You come away with a sense of wonder, a deeper appreciation for how beautiful and complex the universe really is.
And on that note, we'll wrap up our deep dive into mass. We hope you've enjoyed exploring these ideas with us. Until next time, keep those notes of curiosity flowing.